Hi everybody, let's focus on this given. I guess that is not, you wouldn't consider that problem as a linear algebra problem, but this is the typical linear system theory problem, right? For a given two functions, right, a and b, compute exponential, right, e to the a times t, right? And we will again use t to indicate time. This is very important in linear system theory, right? And okay, this is a standard problem, right? And for that, we need to have either diagonal form. If we cannot have diagonal form, we need to have Jordan canonical form of that given matrix, right? Square matrix. And so we need to find diagonal or Jordan canonical form. But whatever the case may be, we are guaranteed to have a Jordan canonical form for a given square matrix. Okay. And this is A matrix, and let's compute the eigenvalues. Here, eigenvalues 3, 3, 3, right? And by the way, this is really numerically, this is not something you will see. I mean, this is like 3, 3, and 3, right? I mean, none of them is like 3.0001, right? It's not like that. And it is the possibility of this being happening, right? Of this being the case is rather non-existent, maybe I would say, right? This is really ill-conditioned problem, right? And that's why Jordan canonical forms are, it is only, we only see in linear system theory courses, I guess, right? They're not that famous, right? And this is the spectrum of A matrix, right? And so we will check that if that is the case. If that is the case, we can diagonalize the A matrix. However, of course, this is not the case. I mean, this is linear system theory course, of course. This is, the dimension is 1, right? And therefore, we will have probably v1, v2, and v3, right? We will something like this type of chain, right? And so let's first compute the proper eigenvector that corresponds to lambda equals 3, right? Here, by using this expression, we can conclude 1, 0, 0, or rather E1, right? E1, so 1 is the proper eigenvector. Okay, and we can call this V1, right? Okay, again V1, V2, V3. Okay, so let's check this, and this is 1, right? And which signifies that there is one Jordan block, and this information immediately allows us to conclude the Jordan canonical form is here in that form, but we still need to compute the transformation matrix, right? And here we need to find v1, v2, and v3, and those vectors must satisfy those given three equalities, right? Again, here this is also something we compute, right? And since this is 3, right, and underlying vector space is R3, again 3-dimensional, right? We can start from the v1, v2, v3, right? We can start from the v3, right? v3 can be chosen one of the basis vectors e1, e2, and e3, right? Okay, we will simultaneously check those three vectors as being v3, and then we will compute v2, and then we will compute v1, right? And there will be one of them correct for v3, right? Okay, Here, let's check them. This is E1, this is E1, and basically I am focusing on this, right? I am focused on this, right? V2, but I don't know what V2 is at this moment, right? And this is E1, this is E1, and that yields 0 vector, and immediately we can say that it cannot be the case where V3 equals E1. This is not, it's out of the possibilities at this moment, right? Okay. However, for E2 and E3, they are not 0, so we can say, yeah, it can be. We're not sure. It can be, right? Okay. And this is V3, right? This is V3, V2 pair. This is V3. Let me delete some of parts, right? This is important. And this is V3, V3. This is V3. This is V3, right? Maybe get another color. Okay. This is V2, V2. This is V2, again V2, right? So the answer is either this or this. We are not sure, right? And one of those pairs, right? And now that we have V1, V2, and V3, now that we have V3 and V2, we will focus on the computation of V1, right? What was the relationship between V1 and V2? This is it, right? So since we have two candidate V2 vectors, we will test them, right? First, this is right here, and we compute and we get 0, and that immediately allows us to rule out that possibility, meaning this cannot be the correct pair, right? And let me get that. Okay. And so the other possibility, this pair must be the correct one. This is the correct one. Okay. So let's compute v1 for that v3 and v2 vectors, and I guess we directly compute it, I guess, right? And this is the, let me get this. This is the v1, right? This is v2 and v3. v3 is here, e3. v3 is e3, and v2 is 1 1 0 here. v2 is 1 1 0. Okay, and this is the v1, this is the v3. Again, we would use something like that type of notation, right? And this is our transformation matrix. All right, I'm explaining incredibly slowly, I'm aware of this, just to allow you to, get that, digest the concept, right? It is simple, but there are some little details, and that's why I spent a lot of time on those details, right? Okay, here we can check whether the Jordan canonical form we computed is the correct one, just to, a sanity check, right? And that is the case. Again, this is not 100% important, but characteristic polynomial of matrix A and minimal polynomial, they can be written like this, right? Okay, and to compute the term e to the at, right? We will use Jordan canonical form of A, right? Here, this is it, and then we will multiply it with the scale of t, right? Here, a times t, and j times t, right? T can, commute with that matrix, right? So this is a times t, right? This is j times t, all right? And here, right? Explicitly we can write this, and then this is the formula we will use, right? And here we will look at this, and we can directly write this, right? And this comes from some, again, something we are kind of expected to know that it exists, not that we need to memorize that, but this type of thing exists, right? So let me get this, recall that, right? For that type of exponential operation, right, we would have this, right? And then we would write this, and then we would write those terms, and then we would write those terms, right? It's like table expansion looking entries, right? And this is something that you would derive, you would kind of persuade yourself into thinking, yeah, this is the correct thing, right? And so basically this comes from the formula, right? Formula we used, right? Okay, and this is the more general one, right? If we have a higher dimension or higher, yeah, size Jordan block, right? This is the thing that we will use. And again, we still need to transform the given matrix, right? Here, this is annoying algebra actually at this moment, right? I just inverted that matrix, and then here I multiply those two matrices, right? And then again we multiply them and arrange the terms, and we get this, right? Okay, so let's focus on the B matrix, right? And again, let's check again eigenvalues 5, 5, 5. Of course, all of them are I mean, there is not even a distinct eigen, two distinct eigenvalues, right? In the spectrum of the B matrix, right? So let's quickly compute the generalized eigenvectors, right? And here, yeah, and this is really good example, right? This is really good example, important example. Here, we would, as a reference, right? Right, something like v1, v2, and v3, right? We will do that, but this is a special case, right? You need to check the dimension of that given null space, right? And if you find this equals 1, and then if you find square of that term, right, the dimension of the null space of the b minus 5 times identity, right, you find this as 2, and gain the same, and also if you find this, then you would get to write that chain notation, right? Chain form. However, we we computed, and we determined that it is not equal to 1, but 2, right? There are two eigenvectors, right? And that's why that's why this is kind of different problem compared to the ones we dealt with before, right? And Since there are two vectors, that means there are, since this is 2, right, this is 2, there will be two Jordan blocks, right? This is something like this, or you can also write something like this, right? Okay, depends on how you write it, right? Okay, and let's focus on at this moment. So this is not like this, however, right, this is something like v1, v2, and omega 1. Yeah, omega 1. This is like that, right? The previous examples in that form, however, this is in that form, right? The geometric kind of summary of that, right? This is not the case, but this is the case, right? Okay, and the we are going to call one of them v1 and other of them w1, right? Okay, I'm looking at this right now. Although I produce those notes, it's hard for me at this moment. I'm a little confused. Wait a little. And this is the constraints, right? Record these. And alright, linear independence. Okay. And yes, let's okay. Let's continue from this location. At this stage, we do not know which one of these vectors, right? This one or this one, right? Must be chosen as v1 and w1, right? Okay. And since we can determine this, right, we can start selecting v2 among the standard basis vectors, right? This is v2. v2 is one of those, right? We will choose v2 as one of the standard basis vectors, and here I'm just writing this basically, right? Here this is v2, candidate v2, this is candidate, another candidate v2 as another candidate v2, and we check the results, and this is 0. Since this is 0, v2 cannot be e1, right? And this is not 0, and this is not 0, so it basically states that v1, v2 can be either, right, this pair or this pair, and we select v1 as 0 1 1, right? Okay, remember 0 1 1, right? Okay, and let me change the color, right? At this moment we will call, for example, this is v2 candidate, this is v2 candidate, and this is v2 candidate, right? We don't know at this moment which one of them is v1 and which one of them is w1. We don't know that, right? And we say that v2 cannot be this, right? And v2 is either this or this, right? And that also implies v1 is either this or this, right? However, we compute our original v1 as this, or rather as one of those vectors, and since you can see here those two vectors are linearly dependent, right? And we can say that, you know what, it is better for us to just call that v1, right? And this is v1, and then that's why this should be named as w1, right? Okay. And all right, by the way, let me tell you, if that was not 100 but 200, right, we would use that as our v1, right? Okay, because we are now going to construct our transformation matrix by using v1, v2, and w1. Okay, all right. Wait a minute, did I make a mistake somewhere? I directly ruled out this possibility. However, it says that we this can. Oh, I made a mistake. Yeah, that's a big mistake. I mean, not 100% mistake, but yeah, I made an assumption. I shouldn't make. All right, let me delete that. We don't know which one is v1 and which one is w1. Okay, right. Because from the information we concluded the geometric formation is something like this: v1, v2, right, and then w1. We concluded the geometric formation is like that. Okay, and we choose three candidates v2s, right, and we computed and we found this is 0, and since v1 cannot be 0 vector, right, v2 cannot be this e1, right. However, v1 can be this vector, and v1 also can be this vector. Okay, and this is like the critical part. This is so critical that I made a mistake a moment earlier, right? And let's look at, you know what, it is better for me to just write down 1 0 0 and 0 1 1. Okay, look at those pairs and that pair, right? Okay, and it is easier to see since I write this, right? And v1 is probably something, I mean, it is like a times a 0 0 v1, something like this, right? Because v2 is either this or this, right? And that's why v1 either this or minus e1, or I'm sorry, plus e1 or minus e1, right? And that's why I am going to call this v1, and I'm going to call this, not that it's important, but this is important actually. I'm going to call this w1, but we are not sure about that v1 if we are going to use that v1, right? Maybe we are going to use minus e1, we don't know, or I mean, there's only two possibilities, plus or minus, right? We will use 1 0 0, or we are not sure, minus 1 0 0, right? We need to check that. Okay, and at this moment I guess it is not important for us to check that. We can use I mean, w1 is 0 1 1. We are, I mean, we know that, we established that, right? w1 w1. However, v1 and v2 can be this pair or this pair, and this is not like the previous problem. It is either this or this. However, it can be, yeah, it can be this, and also, you know what, it can be this. You can, I mean, you have the, degrees of freedom at this moment, right? You have that kind of a freedom. You can, if you want, you can use this, or you can use this. It doesn't matter, right? Okay. So let's use that, right? Let's use that, and let's use that here. So we have two transformation matrix, right? If you can compute the Jordan canonical form, you would get two different. I mean, you know what? This is why, that happens. Let me tell you. Okay, what was our Jordan canonical form matrix? Yeah. Do you remember? I told something like this. It can be like that, right? Or it can be in this form, right? 5 1 5. And since there are two ways of writing that, it is not impossible to think that there will be two different transformation matrices, right? So there will be two different v1, v2, and w1, and v1, v2, w1 triplets, right? Triplets, right? That is the source of the problem, or I mean, it's not the problem, but yeah, source of the phenomenon, I guess, right? So let's use that, right? We can either use this or this. This, however, let's use this. This is choice. Doesn't matter, right? And this is the transformation matrix. And here we can find our transformation matrix and our Jordan canonical form here in this form, right? Okay. And this is the characteristic polynomial. Not that it is very important at this moment. And here, this geometric multiplicity is 2. Why? Why? Because the dimension of the null space of, right, A minus, this is B matrix, lambda, and that lambda is 5 times identity, right? This is 2, right? That's why we concluded that the geometric multiplicity being 2, right? Okay, let's continue. Again, the same operation that we did for the matrix A, right? Here we written down this, and again B times T, right? Here let's write explicitly B times T here in that way, right? And then let me zoom a little, and now we need to compute this, right? Here we need to compute this, right? And it says, let's first focus on the term this, and since this can be written in block diagonal form, right? We have this, right? And we can consider the atomic parts of that given matrix, right? Here, just focus on this, it says, and by using our formula, right, we can directly write this, right? You can write that down from looking at some given table, right? Okay. And therefore another one is just a scalar, right? So you can immediately write something like this, right? Okay. And therefore here also you can write this exponential, right, term, And I'm looking at this. This must be 0. This is a typo, right? This is typo. And here we concluded that. And now we are going to do that transformation, right? The similarity transformation. Here we can write our transformation matrices, right? And we inverted that. And let's multiply them, and then we can find that matrix, right? And then here this is the final solution, right? Okay, and let me check this. Yeah, this right. I'm very happy right now. I concluded all 7 problems, and yeah, that was a simple but typical, stereotypical linear systems theory problem. E to the a times t, right? And we will use that type of object, linear algebra object, in the computation of state transition matrix and some other related terms, right? We'll be focusing on more on them later, and this will be a playlist, right? There will be other videos, so let me write something, right, to be continued, right? Dot dot dot. Okay, and thanks for watching. By the way, before ending the session, right, I want you to look at only these 3 lines, right, for the A matrix, right? For the A matrix, just look at this, focus on this part, right? If you want to, and you should want to, right, and compute e to the a times t, right, you should just run these 3 lines, right? This is symbolic toolbox computation, and this is our A matrix, and exp m is important because otherwise it would, if you write something like this, right, it would give you e to the each entry of that matrix, right? Okay, and that is the answer. That is the answer. So that's why you should be happy that you have MATLAB and something like that type of computation tools, right? Otherwise we would be dealing with that type of operations, and they are really, make no mistake, they are really cumbersome operations. I mean, even though this is like 3 by 3, right, it is really, it took a lot of times, right? Imagine what would happen if we have had like 10 by 10 or 20 by 10, right? 20 by 20, right? That type of dimension, that would be really, I mean, impossible at this moment, right? Okay, and that's the conclusion. Thanks for watching.